Hello friends, this is a lecture series on the Special Theory of Relativity. Part 1 emphasizes on analyzing problems on time dilation. The Special Theory of Relativity emphasizes some key concepts. First, we have space and time exist within the universe. Space and time are two parts of one whole called space-time. According to Einstein's theory of relativity, time is affected by motion in space at constant velocity. Time appears to pass more slowly in a frame of reference that is moving relative to the observer. An inertial reference frame is one in which Newton's law of inertia is valid. There are two postulates where the special theory of relativity is based upon. The first postulate states that all the laws of physics are the same in all inertial reference frames. Postulate number 2 states that the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. Before we introduce the time dilation equation, let us first look at this figure, which shows two observers. Observer 1, Mavis, she observes a light pulse emitted from a source at O' and then reflected back along the same line. So as shown in the diagram, the first event is when light is emitted by the source, right? Then the light, of course, travels towards a mirror and gets reflected back to exactly where it was emitted. All right? So, according to Mavis, who is in the frame of reference denoted as S prime, according to her, the time interval that it takes for light to travel from the source O prime to the mirror and back to the same source is measured by delta t sub naught. Another observer, okay, in the S frame of reference, Stanley, he observes the same light pulse, but following a diagonal path. Okay, so the first event, when light is emitted from the source, same source as what Mavi has observed. Okay, but since from Stanley's frame of reference, right, the mirror is moving together with Mavi, who is inside the frame of reference S prime, is moving at a velocity u. So from Stanley's point of view, the distance traveled by the light, okay, from the source O prime to the mirror is denoted here by L. And when it comes back, okay, to the source, it's no longer exactly at point O prime, but it's now at a distance defined by U delta t, where delta t is the time that it takes light to travel from the source to the mirror and back to the same source, that have been moved through that distance. So, according to Stanley, the light pulse travels at the same speed, okay, as in uh, the reference S prime, but it travels a greater distance than in S prime, right? So the distance traveled by the light is denoted by the product of U delta t. So he concludes that the time it takes the light to travel delta t is longer than what Mavi has observed. We say that delta t is greater than delta t naught. So, in the time dilation equation, all right, if two events occur at the same space point in a particular frame of reference, the time interval delta t of naught or t naught between the events as measured in that frame is what we call the proper time interval. That is denoted by delta t naught. If this frame moves with constant velocity u relative to a second frame, the time interval delta t between the events as observed in the second frame is longer than delta t naught. So in the formula, the time dilation, or the time that is dilated or lengthened, is denoted by delta t, while the delta t naught is what we call the proper time interval. Okay. Uh, Letter U stands for the constant velocity, all right, of the moving frame, moving relative to the second frame. Okay. Of course, c is the speed of light. So the denominator in this equation, right, square root of 1 minus u squared over c squared, the reciprocal of that is also known as Lorentz factor, denoted by the letter gamma. So the Lorentz factor gamma is equal to the reciprocal of the square root of 1 minus, okay, u squared over c squared. So the time dilation formula can also be expressed in terms of the Lorentz factor gamma, or delta t is equal to gamma multiplied by delta t naught. Okay? The meaning of each quantity is defined such as delta t. It is the time interval between the same events measured in the second frame of reference. So delta t without the subscript 0 is what we call the dilated time, right? While delta t with a naught, subscript naught, is defined as the proper time between the two events measured in rest frame. Of course, gamma is what we call the Lorentz factor, equal to the reciprocal of the square root of 1 minus u squared over c squared, where u, letter u, stands for the velocity or speed of the second frame relative to the rest frame. And of course, c is the speed of light in vacuum. All right, before we go to some conceptual questions, let's first talk about the time dilation equation. Delta t is equal to delta t naught divided by square root of 1 minus u squared over c squared. We say that time is relativistic if the speed of a moving body is very much near the speed of light, right? So if u is almost equal, but not equal, almost, as delta u approaches the speed of light, then the delta t will be considered a relativistic time. That means the formula is valid. Okay? We will have a denominator that will make the value of delta t greater than the value of delta t naught. Okay. If the value of the speed of the moving body is very much lower than the speed of light, okay, to the point that the ratio u squared over c squared is almost equal to 0, then we will have a denominator that's exactly equal to 1. And that would mean that delta t is just numerically equal to delta t naught. So in which case, there is no what we call relativistic time that will occur. If the speed of the body is much greater than the speed of light, we will result to an imaginary number in our denominator. So, this implies that no physical object can ever move faster than the speed of light. It looks like the speed of light is already the maximum speed. The value of c sets the limit for all moving objects in the universe according to the special theory of relativity. Here are some conceptual questions that we will address. Number 1, can you travel while remaining in one place in space? Number 2, does light travel through space? Does it travel through time? Does light travel through both space and time? And question number 3, what does it mean to say that motion is relative? Our answer to the first question is yes, we can travel while remaining in one place, space. That means traveling in time. For question number 2, the answer is light travels through space but not through time. Neither can light travel through both space and time. And for question 3, when we say motion is relative, we simply mean that motion is with respect to a frame of reference. For problem number 1, the muon is an elementary particle that decays into an electron and two neutrinos. The neutrino is another elementary particle. In an average of 2.2 raised to the negative 6 seconds when it is at rest. What average muon lifetime does an observer find when a beam of them moves past her at a velocity of 2.9 times 10 to the 8 meters per second? So our solution, okay, we first identify the given data. The proper time or the lifetime of the muon particle at rest is given 2.2 times 10 to the negative 6 second. Okay, we are required to find, okay, the delta t, which is the time dilation. All right. Also, we are given the velocity, average velocity of the particle muon, which is u is equal to 2.9 times 10 to the 8 meters per second. Before we proceed in calculating for delta t, let's determine already the ratio of u over the speed of light c. That means 2.9 times 10 to the 8 meter per second divided by the speed of light, which is 3.0 times 10 to the 8 meters per second. So the ratio becomes 0.9667. And of course, squaring, okay, the two quantities, or u squared over c squared, we simply square this value 0.9667 to get this ratio of the squares equal to 0.934. And solving for delta t using the formula for time dilation, delta t is equal to delta t naught divided by square root of 1 minus u squared over c squared. Since we already have determined the term u squared over c squared, which is 0.934, we just plug in the formula to get for the value of delta t naught, which is 2.2 times 10 to the negative 6 second, divided by square root of 1 minus 0.934, and we will get as our answer for delta t, alright, is equal to 8.6 times 10 to the negative 6 seconds, which as expected, okay, the delta t, the value of the delta t is a lot greater compared to the value of delta t naught. For problem number 2, what must be the velocity of spacecraft if 1 hour on its clock is to correspond to 1 hour plus 1 second on a clock on the Earth? Right, so our solution, we have the following given data. The delta t naught, or the lifetime at rest, is equal to 3,600 seconds, while the delta t, meaning the clock on the Earth, is equal to 3,601 seconds. We are required to find, okay, the velocity of the spacecraft, labeled as u. So from the formula of delta t equals delta t naught divided by square root of 1 minus u squared over c squared, okay, we are supposed to determine the working formula for us to be able to find u. Alright, so if you derive this or transpose the quantity u, alright, you will come up with the working equation. U is equal to speed of light multiplied by the square root of 1 minus t naught squared divided by t squared. Okay, so in this working equation, we also have not included the symbol delta. So t naught here is supposed to be delta t naught, and t squared is supposed to be delta t squared. So we just remove the symbol delta. It's understood that what we mean by t naught is the delta t naught, and t squared is for delta t. So substituting the given quantities in that equation, we have speed of light 3 times 10 to the 8 meters per second multiplied by the square root of 1 minus, okay, the square of t naught, where t naught is 3,600 seconds, divided by the square of t, which is 3,601 square. And we will get, all right, the value for u, or the speed or velocity of the spacecraft, equals 7.1 times 10 to the 6 meters per second, right? And as expected, okay, the value of u is a lot lower than the value of the speed of light. Problem number 3, using the formula for time dilation, how long would it take a person traveling at 99% the speed of light to travel to the star Procyon, which is 10.4 light years away? So, for our solution, we identify the given data. First, we have the delta t, which is 10.4 years. This is the time, or the time it takes for the astronaut who will be moving at the speed of light, 99% the speed of light. Okay, so this is from the perspective of an observer on Earth. Okay, the delta t is 10.4 years, right? What we are asked is to find the proper time, or delta t naught. Okay, this is the time it takes the person from his, okay, frame of reference, right? How long it would take him to reach the star Procyon, which is in fact 10.4 light years away, right? So before we go into the actual computation for delta t naught, let's already simplify our computation by first getting the value 1 minus u squared over c squared, where u here means 0.99 the speed of light. All right, that is the speed of the person traveling in that spacecraft. But you have to square it and then divide it by the square of the speed of light. And what we get is 1 minus 0.9801, which is equivalent to 0.0199. We need this in order to get the value of delta t naught. Okay, from the original formula of delta t, we can derive the working formula for delta t naught, which in fact is equal to t naught. Already the delta sign has been removed. All right, so t naught becomes t multiplied by the square root of 1 minus u squared over c squared, where the term inside the radical sign has already been simplified to be equal to 0.0199. So all we need to do is multiply the value of t, which is 10.4 years, right, multiplied by the square root of 0.0199, and that gives us, for the t naught, which is 1.47 years, right? So from the perspective of the person traveling at the 99% the speed of light, okay, for him to be able to reach the star Procyon, it would take him 1.47 years from his frame of reference. But from the reference of an observer on Earth, it would take 10.4 years. And as expected, the proper time, all right, or the time at rest, T naught is equal to 1.47 years. Right. So we summarize. From the Earth, the trip would take 10.4 years. Right? Because the ship is traveling at almost the speed of light. In other words, uh, the relativistic time formula, okay, is applicable in this situation. However, on the ship, the trip would only take 10.4 years times the square root of 1 minus 0.99 squared, or as computed, it will only take 1.47 years, okay, for the person traveling at 99% of the speed of light to reach the star Procyon, okay, a much smaller length of time, only 1.47 years. This is not the last problem. Dawson and Brayden are 20-year-old twins living on Earth in the 25th century. Dawson, who is a space traveler, flies to the star Altair about 17 light years away at a velocity equal to 0.90 the speed of light, c. Then he returns to the Earth at the same speed. Question: what are the ages of the twins when they meet again? So our initial solution, we say that Altair, star Altair, is 17 light years away. So Dawson makes the round trip in a time as measured by his brother on the Earth, okay, equal to t, which is 34 light years, okay, or 34 years multiplied by the speed of light, all right, divided by 0.90 c, right? And what we get for our time t is 38 years. So it would take 38 years for a dozen, okay, to make the round trip uh, as measured by his brother Brayden, who is left on the Earth. Okay, take note, 38 years. That is the value for uh, time t. This is the supposed to be the delta t, or the time dilated, and that is related to the delta t naught, okay, because 38 years, which is the delta t, is just equal to the value of delta t naught divided by square root of 1 minus 0.90 squared. And the value t naught, which is the time that passes in Dawson's reference frame during the trip, can be calculated now as 38 years, okay, multiplied by the square root of 1 minus 0.90 squared. And doing your math, we will get the value for t naught, which is 17 years. Thus, our conclusion is, when Dawson returns to the Earth, he is physically only 37 years old, while his twin brother Brayden, okay, is now 58 years old. This is the result of uh, the time dilation, okay, formula. Dawson, who went on space travel, Okay, he left at the age of 20, right? But from his perspective, he has been away for 17 years. So he is physically 37, 17 plus 20. He is physically only 37 years old, while his twin brother, who was left behind on Earth, okay, when he left, his brother Brayden was also 20 years old, right? But um, he is now, okay, when they met, Brayden is now 58 years old because uh, from Brayden's frame of reference, all right, his twin brother who went on space travel has been away for 38 years, all right? When he left 20 years ago, right, then plus 38 years, a total of 58 years. Therefore, Brayden is physically 58 years old, much older than his twin brother Dawson, who went on space travel. So this is known as the twin, or yes, we call this, all right, the paradox. Because of time dilation, Brayden sees Dawson's heartbeat and all other life processes proceeding more slowly than his own. Thus, to Brayden, Dawson ages more slowly. When Dawson returns to Earth, he is in fact younger, or has aged less, than his twin brother Brayden. Now, here is the seemingly paradox. All inertial frames are considered equivalent. Can't Dawson make exactly the same arguments to conclude that his twin brother Brayden is in fact the younger? Then, each twin measures the other to be younger when they are back together, and that's what is called the twin paradox. Okay? The key concept is that all inertial frames are equivalent. Okay? So, how is this seemingly uh, paradox? Okay? When you say paradox, it is like a, a false statement that appears to be true, or a true statement, okay, that appears to be false. How is this resolved? Okay, to resolve the paradox, we have to recognize that the twins are not identical in all respects. When Brayden remains in an approximately inertial frame at all times, Dawson must accelerate with respect to that inertial frame during the parts of his trip in order to leave, turn around, and return to Earth. Brayden's reference frame is always approximately inertial. Okay? Take note that Brayden stayed on Earth, so he is in an inertial frame of reference. Dawson is quite far from being in an inertial frame. Thus, there is, in fact, a real physical difference between the circumstances of the two twins. Careful analysis can show that Brayden is in fact correct. When Dawson returns, he is younger than Brayden. So, to some, okay, the so-called twin paradox, after all, is not a paradox, but it's just the result of having uh, two events happening not simultaneously. And the fact that Dawson, who went on space travel, is in fact, okay, not in an inertial frame of reference because of the accelerations involved, okay, partly during his travel. But the truth is, when they met, in fact, the twin was left on Earth, okay, is already older, a lot older than the twin that went on space travel. So, that's all for now. Thank you very much.